the recording. So this is section 7.3. This is the fundamental theorem of calculus. Okay, and this is the last section we're going to do on integration. There's a whole lot more that we could do, but we don't have time. I encourage you to read the book. In particular, section 7.4 is quite interesting. It's called the Darboux integral, and it's a nicer way to do this stuff. The problem is it doesn't generalize. So the Riemann integral that we're doing generalizes quite well. So in some sense, it's nicer to know this. Okay, we're skipping section 7.2. And the main result there's a lot of results in there, but the main result is that continuous functions are integrable. Okay. It actually turns out if we had taught the Darboux integral instead of the Riemann one, then that's a pretty easy theorem to prove. Given that we taught the Riemann integral, it's a difficult theorem to prove, and I'm really unhappy with how the book proves it. So that's kind of that's my reasoning. The fundamental theorem. Well, okay, so yes, Benjamin, the fundamental theorem does apply to all the integrals. We'll be proving it for the Riemann integral today. Okay. So anyway, like I said, I will cover section 7.2 in an extra lecture at some point over break, and you can watch it whenever is convenient to you. Okay. So, on to the fundamental theorem of calculus. There are two parts. I'm sure you saw the fundamental theorem of calculus in your Calc 1 class. Both parts of it tell us that integration and differentiation are opposites of each other. Okay, so one part says you can undo differentiation by integrating. The other says you can undo integration by differentiating. Now, I actually went and checked in all the calculus books I've ever taught out of. It's a pretty weak theorem in the sense that the hypotheses are really demanding. Okay, so we're going to prove a better version of the fundamental theorem because our hypotheses are going to be weaker, and we'll talk about that as we go. Okay, so once again, there's two parts to the fundamental theorem. I am going to follow the book's labeling. So I'm going to start with what the book calls part 1, but Wikipedia disagrees, and I tend to believe Wikipedia over books. Wikipedia says this is part 2, so we can definitely agree it's a part of the fundamental theorem of calculus. And what it says is that you've got two functions, a little f and a big F, and they satisfy three things. One is that the big F is continuous. On the closed interval, a to b. Oh, is my audio having problems?
Yeah, randomly it's like cutting out when second.
There we go. Restart the recording. Let me know if you have any problems with this.
Just a question. So lowercase f is the original function, and then capital F is the integral, right?
Yeah, you should think about it that way. Yep. In fact, here, part 2. The rule is that f prime, so capital F has to be differentiable, and it has to be little f of x for all x in the open interval. And part 3, f has to be Riemann integrable. And your conclusion is that the integral from a to b of little f is capital F at b minus capital F at a. So like I said, that's part 1 of the fundamental theorem. I think we're only going to prove this part. We're not going to prove part 2 today. Then you can see we're, on the left-hand side, we're integrating the derivative, and on the right-hand side, we're getting the difference of the integral. Okay.
On number 2, is there a reason we're working with the open interval a to b?
Yeah. Because in general, we're not taking derivatives at the endpoints ever. Okay. The other thing, actually, sorry, there's one more reason for that. If you look in the book, they point out that actually this is going to hold even if you have a finite number of exceptions to that, to number 2. And the reason for that is if you have a finite number of exceptions, let's say this is our real line, let's say we had an exception there, then you just paste together the fundamental theorem of calculus for each of those exceptions. Okay. Any other questions?
I find it interesting that the right-hand side looks curiously like the mean value theorem. I don't know if there's a connection though.
Oh yeah, that's really good. Yep, there is. That's how we're going to prove it. Okay. So let's go into the proof. Like I said, this will be our one proof for today. Okay. What are we trying to prove? We're trying to prove something about the integral of f. Okay. And we're given that it's Riemann integrable. Oh, that reminds me, there was something I wanted to say here. The result we're skipping over, but which you should assume for today, is that continuous functions are integrable. So if little f is continuous, then everything's going to be fine. Okay. But anyway, in terms of the proof, we're given that it's integrable. We want to prove something about the integral. So what does it mean to be integrable? It means that if we fix any epsilon, since little f is integrable, there is a delta which depends on epsilon. Let's keep this hypothesis, I guess, as long as we can, such that the difference between the Riemann sum of any tagged partition P with norm less than delta, I'll write that afterwards, the difference between that and the integral is less than epsilon. And let's see, I have to write for all tagged partitions P dot with norm less than delta. Okay? We've used one of our hypotheses. Now, let's take a partition, not a tagged partition. So let's just let P be a partition. Usually we write partitions as this. And this is a non-tagged partition. That just means we haven't picked the points where we're going to evaluate the function at. And let's take it with norm less than delta. So what we said above was any way we go and tag that partition, we're going to be within epsilon of the integral. Or Riemann sum is going to be within epsilon of the integral. Okay. We had three hypotheses. What one haven't we used? Or what we haven't used two of them. We haven't used 1 and 2. So f is continuous on the closed interval AB, and it's differentiable. Okay. Well, if you're continuous and differentiable, we can apply the mean value theorem. So let's do that. By the mean value theorem applied to f on each interval, we're going to apply it on these intervals, the little sub-intervals of the partition. What we can do is it says we can always find a point where, well, I'll just write it. Okay. Okay, we can find a point where f at the end minus f at the beginning is equal to the derivative of f at that point times the difference. Okay. And then we know that the derivative of capital F is little f. What does that remind you of?
It looks like a dx, I guess, even though it's not really.
Mm-hmm. So that looks like a delta x.
Right. I guess we're taking our partitions weighted by our tag.
Yeah. This looks like f at a tag. Okay. So what this looks like is the inside of a Riemann sum, right? So let me see, which way do I want to explain this? Let me do it this way. we also have I see. I want to do it this way. Okay. Therefore, let's sum all these guys up. Okay, so I want to sum f at the ti's times the delta xi's, or if you don't want to use the delta xi's, they're these guys, xi minus 1. Okay, well, by our calculation above, actually this is by the way we pick the ti's. This is just f, capital F at xi minus capital F at xi minus 1. Okay. Now what can you say about that sum?
All of the inner terms will cancel out.
Yes. What do we call that?
Telescoping?
Yes. It's a telescoping sum. So I haven't written much of it, but there you go. That's what's happening, and then the f of x2 is going to cancel with something over there, etc. So only the first and last, only the f of x naught and the f of xn are not going to cancel. So this is equal to f of xn minus f of x naught, and that's just f of b minus f of a. Okay, so if we take those t's to be our tags, so taking the ti to be our tags to form a tagged partition, our tagged partition would be p dot, which is p together with this set of tags, t1 to tn. Okay, what do we see? We see that the Riemann sum for that tagged partition is actually just f of b minus f of a. We chose the partition so that its norm is less than delta. And what we said was that for any tagged partition with norm less than delta, we're going to be within epsilon of the integral. Okay. We write that down. We have that since norm of that tagged partition is less than delta, the distance between this, which again, that is just the Riemann sum of f with respect to these tags, minus the actual integral is less than epsilon.
Professor,
Yeah.
could you remind me of what you mean when you write S of F semicolon P dot?
Oh, yeah. Well, this is the this is the Riemann sum. F at the tags times the delta xi's, or the xi minus 1. Okay.
Got it.
Where P dot is this complicated tag partition. The partition, which again, the partition was the that specified x naught, x1, etc. up to xn, and then the tags tell you the t's. Okay.
Mm-hmm.
Okay, so now, well, we wanted this quantity to be equal to the integral. How do we finish our proof? Any volunteers?
Well, I mean, everything we picked was somewhat arbitrary, so it seems to follow that f of b minus f of a minus the integral has got to be 0.
It's not that everything we picked is arbitrary. It's that one thing we picked is arbitrary.
Well, epsilon.
Yes.
Epsilon's arbitrary.
Epsilon is arbitrary. Okay, so since epsilon is arbitrary, we can make that difference as small as we want, so they have to be equal. Okay, that's a standard conclusion to so many of our proofs. Because epsilon is arbitrary, this implies that we actually have equality there, proving the theorem.
We just lost your iPad.
Yep.
I had lost it for a minute.
The recording. Okay. Okay, well that's the end of the proof. So now let's take a second and go back over it, because I know we had some interruptions in there. The key takeaway from this is it really is just the mean value theorem. Let's go back up. So our hypotheses were that we have two functions. We'll call them the big one and the little one. The big one has to be continuous, and the little one has to be the derivative, and the little one has to be integrable. And then the theorem says that, well, it tells us the definite integral of f from a to b is the difference in the big one between a and b. Okay, and the proof was, we were trying to prove that in an integral, so you said so Benjamin says the third hypothesis seems too strong. Can't we say it's just continuous? So remember, the theorem we skipped, but I want you to keep in mind, is that continuous functions are integrable. So if you are continuous, then you're definitely integrable. Okay, so we've weakened the condition. We've gone from demanding continuity, as it is in Calc 1 books, to just demanding integrability. Okay,
Okay, that makes sense. I got it backwards, right?
Yep. So the reason Calc 1 books don't demand integrability is that they don't discuss integrability. Right? That's why all throughout calculus you're always saying, assume the function is continuous. So for example, we could handle little f being a step function, because a step function would be integrable. Okay, but Calc 1 couldn't really technically handle little f being a step function because it's not continuous. Okay, or we could handle little f being piecewise continuous. Okay, so it's just, from here to here it's this function, from here to here it's this function, and so on. We could handle that in Calc 1. Technically you couldn't. You'd have to paste together a bunch of integrals to do that. Okay.
Could you explain the little diagram you have of the of how you have the finitely many exceptions to 2?
Yeah.
Can you, now that we've gone through that, the proof, can you explain a little more about that?
Sure. So you've got, here's A and here's B, and there's some places where, let's just have 2. We'll have 2 cuts. We'll call them I don't know, alpha and beta. Those are 2 places where, so at those points, f prime does not equal f of x, or maybe f prime just doesn't exist. Okay? And otherwise you've got the conditions. And now you want to evaluate the integral from a to b of f. Okay? Well, the point is, you've got the hypotheses of the fundamental theorem from A to alpha. Okay, because capital F is continuous there. Alpha and beta are the only exceptions to 2, so in there, there's no exceptions to 2. And little f was assumed to be Riemann integrable everywhere, so it's also Riemann integrable there. And then from alpha to beta, you've got the conditions, and then from beta to b, you've got the conditions. So let me just erase this and write what you can conclude. You can conclude on all 3 parts that you have what you want. Okay, and now if you sum all the things on the left hand side, you'll see you get the integral from a to b. And if you sum on the right hand side, you'll see that it telescopes, and all you're left with is f of b minus f of a.
So a quick question. We didn't necessarily do a proof of it, but being able to add these together to equal the integral across, I imagine it's probably, it's just putting the sums together, but you never know, there might be some like technical trickiness. Is it just as simple as it seems, or is there something that, like a technical trick that is tricky, I guess?
Right. So so I was hoping to just appeal to common sense on that one. Which I shouldn't do. That's a terrible thing. You're right, we haven't proved that theorem. Okay, so what's the theorem we want? We want if f is Riemann integrable from a to b, and c is a point in there, then, well, what do we really want? We want a theorem that says f is Riemann integrable from a to c, f is Riemann integrable from c to b, and the integral from a to b of f is the integral from a to c of f plus the integral from c to b of f. Right? That's the theorem we want. This is what you were saying, right, Daniel?
Yeah, this is exactly what I'm saying.
Yeah. And you're totally correct. We did not prove that theorem. It's in section 7.2. So that's another theorem that I owe you a proof of.
One question.
Yeah.
So for the first two conclusions that you wrote there, are there like cases of functions that are not integrable on subsets of the original, like subintegrals of the original integral that it's integrable?
Right, not at all. There are not functions like that, because this is all true. What I've written is true, but we haven't proved it.
Okay.
So yeah, there's actually two results we want to prove. I'll circle each of them. Right, there are the two circles there. One is if you're integrable on a big interval, then you're integrable on all its subintervals. The second one is that we can paste together these integrals and get an integral over a big interval. Okay.
And those
So-
are just in 7.2, right?
Those are in 7.2, and I owe you proofs of them.
Okay.
So, the way I stated the fundamental theorem of calculus does not depend on this. What depends on those things that I haven't proved is this extension of the fundamental theorem to finitely many exceptions to part 2. Okay?
Okay, that makes sense.
Okay, any other questions before we
Could you show the end of the proof? I never got to see it.
Oh, okay. In fact, let's just go through the proof. Let's review real quick. We wanted to prove that an integral was equal to something. And so the only control we have over integrals is that because it's integrable, because little f is integrable, any Riemann sum we form is going to be close to that integral. So that's what we did. We let epsilon, we got to pick our epsilon here. And we let it be arbitrary because we're going to want to let it be go to 0. Then we got some delta that'll let us get within epsilon as long as our norms are less than delta. We took any partition. We could have right here where we took a partition, we could have actually said what one we want. Right, but we didn't care. So we just took any partition we wanted. And then the big key to the proof is we just applied the mean value theorem to capital F. Okay. When you do apply the mean value theorem to capital F, you get this great thing where the difference of capital F on these subintervals is given by a term in a Riemann sum. Okay, this actually only happens for the Riemann integral. It doesn't happen for the Darboux integral. So for the Darboux integral, this is a harder theorem to prove. Okay, so we said that we're going to take those as our tags, form the Riemann sum. Everything will telescope. We'll just get what we want. And there is the end of the proof. The two things we want to be equal are less than epsilon, and since epsilon was arbitrary, the only way that could happen is if they are equal to each other. Okay. And once again, the big difference between what we did and what you do in a Calc 1 book is we weakened, in Calc 1 usually that little f has to be continuous, and we said it only has to be integrable. Okay? Now, any final questions on this? I was going to do a couple examples just to remind you. I mean, you know, you remember this from calculus. Let me just remind you which theorem we're doing here. If capital F of x is cosine x, then what should little f of x be? Negative sine x. Then we know that the derivative of capital F is little f. Okay. Let's go back up to those hypotheses and check. That was one of them. What about the others? Capital F is cosine x. That is definitely continuous. We just said that its derivative is negative sine x. And then this part 3 is negative sine x Riemann integrable. Well, if you believe the result that we skipped over from 7.2, then yes, it is integrable because it's continuous. Okay? So therefore, what does the theorem say? If we integrate, say, minus sine x from 0 to pi, we'll get cosine pi minus cosine 0, which is minus 2. Okay. So, you know, without the fundamental theorem of calculus, I think it's safe to say calculus would be, I mean, completely horrible. Because up until this fundamental theorem, we haven't had a way to evaluate this except for approximating Riemann sums. Right? Oh, Madeline, why do we need capital F to be continuous? It's because we used the mean value theorem on it. Okay. The other thing is, if you think about it, if you're going to be an integral of a function, you have to be continuous. Okay. Integrals just can't help but be continuous. Okay. Now, we've only got 4 minutes left. There's a whole another part of the fundamental theorem. Fortunately, I've timed it right, so you can't even be surprised that we're not going to prove it. Part 2. If little f is Riemann integrable, we needed that for part 1 too. Then we're going to actually define the function capital F in this one. Capital X we're going to define as the integral from a to x of f of, I had to use a new variable, so u. Is continuous. Oh, sorry, this is, I hadn't even thought about that. This is exactly what I was saying about Madeline's question. This is continuous on the closed interval a. Okay. Okay, so that's what I said. If you are an integral, you have to be continuous. And furthermore, if f is continuous at some point in there, then capital F is differentiable there. And you could probably guess what its derivative is. Okay. What is this function called? Any volunteers?
The antiderivative?
I'm going to say no.
Oh, darn it.
So by the fundamental theorem of calculus, it's the antiderivative. But what would we call it when we just present it like that?
Sum.
What's that?
The Riemann sum.
No, it's not. It's not a Riemann sum. It's an integral. I'll give you a hint. What word goes in that blank?
My gut says sliding. Or like
Sliding's a good word, but that's not it. So there's definite integrals and there's indefinite integrals. Oh, Roger has it. And this is the indefinite one. Okay. Indefinite because where it ends is not specified really. Right, you can put in an arbitrary x there. Okay. And then what does this theorem say? It says that the indefinite integral is the antiderivative. Right? It's the function whose derivative is the little f. Okay, so this I think is saying that capital F is the antiderivative. Of little f. Okay. So the theorem is saying the indefinite integral of little f is the antiderivative of it. Now, as long as the hypotheses hold. And the second part only holds if our little f, the function that we're integrating, is actually continuous at that point C. Okay, so this part 2 of the fundamental theorem says that indefinite integrals are always continuous, but then also if the function you're integrating happened to be continuous, then the indefinite integral is differentiable at that point. Okay. And once again, in a Calc 1 book, usually you require that f be continuous on AB. And you can just check if you require that f is continuous, then you will get that it's Riemann integrable by the theorem that continuity implies integrability. And you'll also get obviously that it's continuous at every point, and therefore the indefinite integral will be the antiderivative at every point in that interval. So if you look back to your Calc 1 book, that's almost certainly the version of the theorem that it had. Our version is stronger because we weakened that hypothesis from continuity to integrability. Okay. So, that's the end of this lecture. Like I said, I'm going to record a lecture and post it on YouTube about the fact that continuous functions are integrable. And I'm going to be posting the homework assignment, but it's not due until a week from Friday. So this is only if you want to get an extra head start on it. Otherwise, have a great break.